I know it's 2026 and most of you are busy building AI agents, writing specs instead of code, spinning up MCP servers, and creating workflows that automate everything. So, in 2026, we are apparently doing everything except the thing we were getting paid to do in 2025, writing quality code. I also know that talking about architecture, protocols, and framework internals isn't exactly the cool thing to do anymore. The cool thing is AI. Your ID is AI, your girlfriend is AI, and your refrigerator is probably raising a funding round as an AI startup. And yet, today we are going to spend the next few minutes talking about internals of Selenium, a framework that has been around for more than 2 decades, survived every hype cycle, and in many ways still defines how browser automation works today. My hope is that by end of this video, you will learn something that no AI generated Selenium tutorial, Medium article, or LinkedIn post about the top 10 AI automation tools is going to teach you. Because frameworks come and go, tools come and go, but understanding how things actually work never goes out of style. Welcome to the Tech Beyond Slop, where we talk about everything that isn't slop. And today, we are tearing Selenium apart to understand exactly how it works under the hood. Whether you are a seasoned estate, a manual tester trying to break into automation, or a developer whose company decided that they don't need QA anymore, you have probably seen this innocent line. Looks simple, doesn't it? For some people, this line brings back fond memories. For others, it triggers flashbacks. Thousands of regression tests running every single day, parallel execution, flaky failures, false positive, passed in Chrome, failed in Firefox, timed out in Safari, crashed in Edge, and Internet Explorer? Well, let's not talk about it. Now, if you have never seen this line before and did not understand anything I said above, here is what it does. In web automation, executing this single line launches a real Chrome browser that can be controlled through code. Think of it like today's AI agents, MCP servers, or tool calling system that can interact with applications on your computer. The difference is that Selenium's world is much smaller. Instead of controlling every application on your machine, Selenium is focused entirely on one thing, the browser. Now, let's come back to my rant. In the last 20 years, we have gone from Cypress will kill Selenium or Playwright will kill Selenium and Cypress both to why write tests at all when AI agents can use Playwright MCP servers and automate everything. Yet somehow, through every hype cycle, every new framework, every prediction of its demise, Selenium is still here. So, how did Selenium become the framework that defined web automation for nearly 2 decades? And more important, what actually happens when this line executes? How does a Java object control a real browser? Why do we need Chrome driver? And why, after all these years, Selenium is still standing? To understand Selenium, we need to go back to 2004. At that time, websites were becoming increasingly dynamic. JavaScript was becoming more common and applications were slowly evolving from single web page into actual web applications. At ThoughtWorks, a developer named Jason Huggins had a problem. Every time the application changed, someone had to open the browser, navigate to a page, perform an action, verify the result, and repeat the entire process again and again. Eventually, Jason had a thought that has probably started half of the software projects on the internet. There has to be a better way. So, he built a small JavaScript based tool that could automate interaction inside a browser. That tool would later become Selenium. Now, if you are imagining the Selenium we use today, forget everything you know. No Chrome driver, no Firefox driver, no Selenium Grid, no W3C standards. The first version, later known as Selenium Core, was essentially a collection of JavaScript commands running directly inside the browser. And for a while, it worked surprisingly well, until browsers started caring about security. One of the biggest limitations was same origin policy. Browsers don't allow one website to freely interact with content of another website, which is generally a good thing. You probably don't want a random blog executing JavaScript inside your banking application. Because Selenium Core lived entirely inside the browser, it was restricted by these rules, and automating real-world applications quickly became difficult. The solution? Selenium RC. RC stood for remote control. Instead of running entirely inside the browser, Selenium introduced a server that sat between your test code and the browser. Selenium RC got around same origin policy by acting as a proxy and convincing the browser that everything was coming from the same website. Behind the scenes, Selenium RC would route the traffic through its proxy, modify HTML response, inject Selenium core JavaScript into pages, execute commands through injected JavaScript. This made browser automation practical, and for several years, Selenium RC became a standard approach. The code would look like this. And if you compare it to the Selenium code we write today, you will notice something interesting. Launching a browser required so many parameters. While it worked, it wasn't perfect. Browsers were still getting control indirectly. Eventually, someone asked a very important question. What if we could talk directly to the browser? And that someone was Simon Stewart. While working at ThoughtWorks, Simon started building a new project called WebDriver. Later, after joining Google, he continued its development and published the early version that would eventually become modern Selenium WebDriver. Unlike Selenium RC, WebDriver rejected fragile JavaScript injection in favor of direct browser-specific control mechanism. During this early era, the browser market was a strict duopoly. Developers were stuck choosing between Internet Explorer, which Microsoft forced upon users like a mandatory family hero, and Mozilla Firefox, the darling rebel fighter of the open source free world. Because at that time, unified automation standards did not exist, Selenium team had to custom engineer deep level, borderline illegal integration workaround for both of these polar opposites. For Internet Explorer, WebDriver bypassed the browser entirely. It used low-level operating system APIs to hijack the application window handle, violently injecting hardware-level mouse clicks and keyboard strokes directly from the operating system. And for the Firefox, WebDriver disguised itself as a privileged browser extension by sneaking into Firefox's trusted internal layer. It gained administrative root clearance, allowing it to comfortably smash right through standard JavaScript sandbox limitations. And finally, browser automation became much closer to how browsers were actually designed to work. At this point, the Selenium ecosystem had two separate worlds, Selenium RC and WebDriver. Maintaining both made little sense, so the projects merged, and in 2011, Selenium 2.0 was released. This is the version most automation engineers would recognize today. So, Selenium 2 solved one major problem. Instead of controlling browsers indirectly through injected JavaScript, it could now communicate with browser through WebDriver. But we are still left with one important question. When we write this code, what actually happens? Let's follow this click all the way to the browser, because once you understand this flow, you will understand most of the Selenium. The first thing to understand is Selenium follows a client-server architecture. This sounds complicated, but it's not. If you have ever called a REST API, you have already understood half of Selenium. Your test code is the client, your browser driver acts as a server, and they communicate using HTTP request. But HTTP is only transport layer. It's the equivalent of saying, I know how to send a letter. That doesn't tell us what's written inside the letter, what language is it written in, and what format should it follow. How do both sides agree on what a request is and what a response is? That's where protocol comes in. The protocol defines the rules of conversation. The drivers needs to know exactly what action I am requesting. Am I trying to click a button, find an element, open a URL, create a browser session? And if something goes wrong, what should the response look like? The protocol answers all these questions, and this is where Selenium's history gets really interesting. Because for many years, Selenium used the JSON wire protocol. Think of it as the original REST API contract for the browser automation. It defined things like how sessions are created, how elements are located, how clicks are executed, how errors are returned. As long as both Selenium and the browser driver understood JSON wire protocol, they could communicate, at least in theory. Because there was one problem. JSON wire protocol was created by Selenium project, not by browser vendors, and every browser vendor had a slightly different interpretation of the protocol. And that's where the fun began. Your flaky tests running in one browser, breaking in other, are kind of issues originated from here. So for years, the Selenium team worked with all the browser vendors to create a common protocol which every browser understood the same way, and finally in 2017, W3C was born, and that became the official browser automation standard. And at the same time, Selenium was also started adopting W3C. Starting around Selenium 3.8, the project gradually introduced support for W3C WebDriver standard while maintaining backward compatibility with JSON web. The remote WebDriver class was re-engineered to act as a hybrid translator. Session started, it performed handshake negotiations. If it connected to an older browser grid or driver, it fell back to JSON wire protocol payloads over HTTP. If it connected to a newer version, it seamlessly spoke the W3C standard dialect. The result, old tests written years before continued to execute flawlessly without a single code rewrite. Then Selenium 4 arrived and finally removed JSON wire protocol completely. From that point onwards, Selenium communicated using official W3C WebDriver standard, and this was much bigger than a simple protocol upgrade. Everyone was finally reading from the same rulebook, and while this may sound like a small change, it would end up becoming one of the most important milestones in Selenium's history, because W3C didn't just replace the JSON wire protocol, it laid the foundation for so many of the features that would eventually redefine what Selenium could do. But that's a story for next video. Now, here is something interesting. If Selenium supports Java, Python, C#, JavaScript, Ruby, and several other languages, was Selenium written in all those languages? Not really. At its core, Selenium is primarily a Java project. Most of the core Selenium implementations are written in Java. So, how does Selenium work with Python, JavaScript, or C#? The answer is language binding. The Selenium project officially maintains bindings for Java, Python, C#, JavaScript, and Ruby. These bindings expose the same Selenium concepts using the syntax and conversation of their respective languages. For example, to click on an element, the code would look like this in Java, in Python, and in JavaScript. Different syntax, same action. But the story doesn't stop here. The Selenium community has also built bindings for languages that are not officially maintained by Selenium project. Go, PHP, Rust. Yes, even Rust. And that's the beauty of Selenium architecture. So, when you write the code to click on an element in your favorite language, then language bindings take your code and converts it to a WebDriver API request, something like this. And that is a standardized WebDriver request traveling across the JSON wire to a browser driver. And that's exactly why Selenium can support almost any programming language. So far, everything we have discussed assume a single test running on a single machine. But browsers don't behave exactly the same. A feature working perfectly in Chrome doesn't automatically mean it would work in Firefox, Safari, or Edge. And if your users are using all those browsers, you probably want to test on all of them. And that's where Selenium Grid comes in. Think of Selenium Grid as traffic controller for browser automation. Instead of sending every test to a single browser on a single machine, Grid allows you to run tests across different browsers, operating systems, and machines. And that's not all. With Selenium Grid, you can run multiple tests in the same browser parallelly, and this reduces the execution time significantly. So far we have talked about Selenium history, client-server architecture, protocols, drivers, language bindings, and Selenium Grid. Now, let's put everything together. Let's follow a single click from our code all the way to the browser and back. So, let's come to the same code. At this point, nothing has happened inside Chrome yet. This is just a Java code executing inside your JVM. The Java bindings now translate this method call into a WebDriver command. Remember, browser don't understand Java. They understand WebDriver request. The binding packages the command into an HTTP request and sends it to the browser driver. Browser driver receives the request. For our example, it is Chrome driver. So Chrome driver validates the request, converts it into browser-specific commands, and forwards it to the Chrome browser. Now, for the first time, something actually happens inside the browser. Chrome locates the element in the DOM, verifies that it is visible, verifies that it is interactable, and performs the click. Once the action succeeds, the browser sends a response back to the Chrome driver. Chrome driver sends a response back to the language binding. The language binding returns control back to the test. But what if something goes wrong? Maybe the element is not present in the page, or element is not visible or not interactable, or maybe it is overlapped by another element. So the browser returns the error. Chrome driver receives it, sends it to the bindings, and then finally we see the exception. Depending on the problem, we can see exceptions like element link intercepted exception, no such element exception, or element not interactable exception. The point to be noted here, the browser doesn't throw a Java exception. The browser sends an error response. The driver translates it, and your language binding converts into an exception that your code understands. This is how pass and fail are actually decided. And that's Selenium. At its core, Selenium is nothing more than a distributed client-server system for sending browser automation commands. Everything else, drivers, bindings, grid, protocols, exist to make this conversation possible. And before you go, I have something interesting for you. Everything we have discussed so far is only half the story. Because for years, Selenium was criticized for being slow, difficult to maintain, and constantly one step behind newer tools. Then Selenium 4 arrived. Suddenly, Selenium could listen to network traffic, capture browser events in real time, talk to browsers using WebSockets, and even remove one of the biggest pain points in automation engineering, driver management. In the next video, we will look at how Selenium reinvented itself, why WebDriver BD may be the most important change since WebDriver itself, and whether playwright is actually winning the browser automation war. Until then, sayonara.